Good evening, everybody. Today we will be starting our live interaction session for the NPTEL course Computational Fluid Dynamics by Professor Srinivas Jayanti of Department of Chemical Engineering in IIT Madras. So I am your TA for this session. There will be two sessions. One is on Saturday and another one is on Monday. The Monday session, 7 to 9, will be handled by myself. I am a research scholar in the Department of Applied Mechanics in IIT Madras. So basically, this I hope I am audible to everyone. You can inbox if you have any doubts or difficulties during the section. Okay, I hope I am audible. Moving
Yes,
forward,
you are audible. Yes.
thank you. Moving forward, uh, in this session, we will be discussing uh, some of the uh, content that is uh, that will make you or help you in understanding the concepts of the course in better way, and also some questions that is similar to the assignments, not exactly, we won't be discussing exactly the assignments, so please don't uh, ask the same. So we will be discussing some questions that will be similar to the assignments, and that will make the concepts more clear. And before starting, let me be clear. This is an graduate level course. That is, you are expected to have a uh, basic graduate level knowledge of fluid mechanics and mathematics to uh, successfully completing this course. If not, if you don't have that, also you can work in parallel and try to uh, understand some core things. If you have gone through the videos, I hope most of you have completed the videos of the first week. So mostly in that we will be you have seen the course itself is starting with an example tutorial problem uh, to give a broad overview of what is the subject. So uh, if you have a little bit of uh, fundamental knowledge about the fluid mechanics, the Navier-Stokes equation, and some numerical techniques, that is mathematics as well as numerical techniques. In most of the graduate level courses, it will be like, undergraduate courses, it will be some numerical methods or something. So all those is that is expected from you actually. So moving on to course contents. This is the broad overview of the course contents. You may have already seen this in the NPTEL website initial page itself. So first week we have already started with the uh, how we can use CFD for the calculation of a flow through a rectangular duct. So let me add. Okay, so first 2 weeks in this course, what we will be discussing is like two example problems to give a broad overview of the course or the subject. So first week we will be discussing about the rectangular duct. Second week we will be discussing about how we can calculate the properties or the flow in a triangular duct. So uh, in the how it differ is like in rectangular duct, uh, the it is more like rectangular is a, the word rectangle itself matches with the Cartesian coordinates, that is rectangular coordinates. So there the discretization of the equation calculation everything will be a lot more easier compared to triangular thing. And then only in our subject in our course we will be checking how some equations or something that is we are taking or solving in the week 1 and 2 sessions, the broad thing, that is the Navier-Stokes equation, how it is solved, or which parameters is what, all such things will be detailedly discussed in the third week. From there onwards, different concepts or different techniques in the CFD is being discussed in the next 2 weeks. And then from week 6 onwards, uh, there is some basic uh, necessities and requirement for the CFD code or CFD tools uh, to give a reasonably good answer. So that's will be discussed in week 6 content. Then moving on to uh, week 7, we will be having solution for compressible force. Till here we will be discussing about incompressible flows. So then comes the compressible force, how the compressibility, when there is compressibility, if it can, if the flow can be compressible, or if the volume can be changed. Such kind of discussions will be done in week 7. Then it will be incompressible force. Then how this algebraic method, there are different methods. I will give you a broad outline after this thing. So how to solve linear algebraic equations, and also there is in week 11 you will be getting a finite volume method, introduction of finite volume method. And the last, we will be discussing about turbulent flows and turbulence modeling. So this is the broad overview of the course. Moving on to the books and references, uh, the course conductor, that is our faculty, and the team itself have given these in the web page. This is some few books. Um, and first one is Computational Fluid Mechanics by Persiger and Peric, and then is Hirsch, then Patangas, Versteeg, and Anderson. So uh, I hope you have a fundamental knowledge and some knowledge of CFD. If not, the better thing is I will give a broad overview of these books also. This Persiger and Peric is kind of little advanced book. So even though it is in the top of the list, so if you don't have that much of a fundamental understanding about the course or the subject, don't go with it directly. And also if you check the some content of this book will contradict with some other things, because most of the this book has the talking from the experimental side also. Then this is also a little advanced book. And the third one, that is Patangar, is entirely dedicated with finite volume method. So these two books, Patangar and Wistik, these two books uh, discuss mostly about finite volume methods. And last one, Anderson. So if I were you, I would have started with Anderson or Hoffman. Uh, Better if you don't have much basics, you can start with Anderson, then move on to Fasigar and Peric or Wirstick. But these two will only, you will be needing these two books, or the content will be used for week 11's course only. So better to start with Anderson, or also another book is there, Hoffman is there, that also you can check. And also there is one book by the faculty himself, that also you can read. So in our course, in our sessions, as I have told you earlier, what we expect is to give you a more clarity of the content by giving you more additional questions and helping you to work that out. So I'll be displaying the questions one by one, and I'll give some ample time, that is around 30 seconds to 1 minute for every question. So you can read the question, then try to answer it, and you can inbox your answers. Please don't turn the mic on. Better to inbox the answers, and you can be wrong also. It's fair. You will learn from your thing. So the first question is: you wish to improve the performance of an air-to-air heat exchanger by designing a better intake manifold because the cold air flow is not uniformly distributed across the heat exchanger. You wish to study this using CFD and arrive at a better design. For this problem, which of the following statement is true? So you have an you are you want to improve the performance of an heat exchanger, and the issue you are facing is that the airflow is not uniformly distributed. So you want to uh, see the distribution of the airflow in the manifold. So for that, if you are using CFD, which of the following statement you expect to be true? Options are: option A, you expect CFD to give reasonably correct solution. Option B, you expect CFD would not be much of use. Option C, you would look for an analytical solution. Option D, you would rather do experiments. So you can inbox your answers. Two persons have already answered. I would urge others also to answer the question. It can be right or wrong. Please try to answer so that this question may be simple, but in coming sessions, if you try to answer the question, even if you are wrong, then you will remember. And also, as you know, the exam for this course is online, so mostly you can only do expect to get multiple choice questions. So mostly the multiple choice question will be confusing. So it is better to clear the concepts through these interactive sections. So all people has responded with an answer A, option A. So let's see what the solution is. Solution is answer A. So let me give you a broad overview of what is CFD, computational fluid dynamics. So suppose here in this problem, what we wanted was there is a heat exchanger, and you wanted to improve the performance, but you want to find the distribution of air across the heat exchanger. So this is your actual problem. So in CFD also, what we are doing is like first there is a problem or some physics. So this physics we are trying to solve using CFD method. So in CFD method, what we are have is a problem. First, we have to understand the physics of the problem. Then we need to mathematical model. That is, model mean in fluid mechanics or in engineering, model means not just a prototype or something. Model means approximation actually. So here you have to approximate the physics using a mathematical model. So this mathematical model can either through differential equations, that is differential model, or integral approach. So integration, differentiation, these are two different kinds of methods or approaches. And also the physics, which is the actual problem, we have to express through these differential equations. This is the second part. So mostly in a CFD, what we will be solving is Navier-Stokes equations. I hope everyone knows about Navier-Stokes equations, or simply written as NS equations. So this is the basis of CFD mostly, because Navier-Stokes is a, a large, I mean, complex equation which cannot be solved directly. So either we have exact solutions for some typical situations, or we will have to do that computationally. We have to solve every parameter. There are multiple parameters inside, variables inside Navier-Stokes, so we have to solve it simultaneously. So that doing it manually is difficult. That's why we need a computer to solve it. That's why CFD exists. So these equations, that is the physics, has to be expressed by Navier-Stokes equation, and Navier-Stokes equation is a big equation which we will discuss in the coming sessions. That has to be up what reduced according to the physics of our problem. So the initial conditions, boundary conditions, all those things has to come into picture. Also the how the flow is there. If you have watched the videos, you will see we are in the first video itself, the faculty is talking about axially developed flow. So that is a reasonable assumption that the through a rectangular duct, the flow in the axial direction will be having upper hand. So we are neglecting the other flows. That's a reasonable assumption. So all such things should be considered while framing our equation to solve. Then this equation should be converted into algebraic equations, because uh, computer can't, or computer or computational process cannot do direct differentiation or integration. It can only do either not to add or subtract. So we have to convert these mathematical equations to algebraic equation. Then these algebraic equation has to be solved to get solutions. So this is the fundamental backbone of the CFD process. And again, if you see here, integrating here algebraic equation, we will be need geometry also. Suppose the flow will be happening here, the flow is happening in a heat exchanger, so we will have to get the domain. What is the flow domain? That is the geometry. So there comes meshing part, and meshing is done to integrate the geometrical aspect of our flow domain into the equations. So this is the overall view of CFD. So that's why the solution says it is, you can expect a reasonably correct solution. Because why it is reasonably correct? Because it entirely depends on your assumptions or the inputs. So if you are making um, any error in understanding your flow of physics, you want, it's highly unlikely that you will ever reach the exact solution. Also, when converting this, because all those stages, suppose I have just drawn some arrows only, but all these times, these conversion, mathematical to algebraic, and algebraic equation to solution, geometry to here, all these conversion, there are a lot of methods. Here will be a lot of methods, here will be a lot of methods. So all these places, the which method you choose, which method you employ, some error creeping into such methods, all of all of those errors can become magnified, and it may result in the incorrect formulation of the result, or you won't even reach the solution. Some people might have heard of diverging CFD solutions are diverging or something. Such conditions are also there. Or sometimes if you are not understand your physics well to model the equation, then the actual solving process even may not start. So you can only expect CFD to give reasonably correct solution, because entire uh, aspect of a good solution is in the formulation. So it will depend on correctness of input. That's where I was wanted to convey the through this first question. Let us move on to second question. I think you have understood the broad aspect of CFD. So, uh, as I have already told you, this course is a graduate level course. May feel some people can feel it is little bit tough, but you have to bridge that gap by reading some additional methods. If you don't know much about fluid mechanics or fluid background, please get some undergraduate fluid mechanics book, and at least read uh, or find the formulation of Navier-Stokes equation and some exact solution of Navier-Stokes equation. So one good book is by Frankum White. So if you can get the book, the Navier-Stokes equation formulation, as well as some exact solution. It is hardly 2 chapters of that book. If you can go through it, if you don't have that foundation of fluid mechanics, please go through that before doing the course. It will help you in understanding the concepts better. Moving on to next question. We wish to solve for steady state temperature distribution in a rod of length L, and the variation is only axial, that is one-dimensional. Which of the following boundary condition combination is admissible? So if you have gone through uh, first week videos, there will you might have heard about two things, that is boundary conditions, short in short BCs, and initial conditions, ICs. So boundary conditions is the condition at which a boundary condition is the condition that exists at the boundary of our domain. So in CFD, we will be calculating, or we will be trying to calculate the flow distribution inside some specific domain. So inside that domain, our flow will be happening, and it will be very much influenced by the boundary conditions existing. So we have to, there are some specific names for these boundary conditions also, which will be discussed in the course. So we have to get the boundary conditions, and also if it is a time varying problem, then we need to have a initial conditions also. So these two set of things are necessary for forming the algebraic equation as well as solving it. So here the question is, which of the following boundary condition combination is admissible? Options, the boundary conditions are: first one, temperature at both ends; second, heat flux at both ends; third one, heat flux and temperature at one end; heat flux at one end and temperature at the other end. And the combinations are: options, statement 1 and 2; option B, statement 1 and 3; option C, statement 1 and 4; Option D, all of them. So here the question is, to solve an one-dimensional temperature distribution problem. So this is the key. One-dimensional temperature distribution problem. Which of the boundary condition combinations are admissible? You can inbox your answers. Thank you. Most of you have answered correctly. So for others, I am just explaining the problem. So we have one single rod. Assume this as the rod. So this is end A, this is end B. So here first uh, first option is temperature at both ends, that we can give T of A is equal to some value C1 constant and TB as C2. That's the first condition. And next condition is heat flux, that is Q, that is dTA by Tx, so assuming it is in x direction. This as a constant or some value. Third option is heat flux and temperature at one end. So heat flux at one end and temperature at the other end. So third option is like at the same end, you can heat flux and temperature. So the other end is kind of free. And fourth option is like heat flux at one end and temperature at the other end. So this heat directly giving temperature to both ends, that is assigning T is equal to a constant. That kind of direct association boundary condition is called Dirichlet boundary condition. And heat flux, that is a what gradient of our variable, that is dt by dx. This is called Newman boundary condition. So these are two types of boundary conditions, and this is easy to solve. Not easy, I am saying this is reasonable, because suppose we know the distribution constant temperature at both ends, then it will be a the in between some distribution will be happening. So it is able we will be able to calculate the temperature distribution. And next one, heat flux at both ends. So here in both ends, if we are giving only heat flux, that is variation of our variable, how the how our variable varies, uh, that is what we are giving, then we can't solve the problem. So we can't take option, second statement. And also you can understand that here we are only saying about one end. So the other end, it is not, that statement is not giving anything about the other end. So these two options we can't take. So only remaining statements are 1 and 4. Then our answer will be option C. So solution for the question is option C. Moving on to next question. Which of the following formulae is a good approximation for the term dou square u by dou y square at grid point I, comma j? Option A is equal, A is u of j minus 1 comma I minus 2 times u of j I plus u of j plus 1 I, the whole divided by delta y square. Option B, u of I comma j minus 1 minus 2 times u of ij plus u of I comma j plus 1, the whole divided by delta x square. Option C, u of ij minus 2 times u of ij plus 1 plus u of I j plus 2, the whole divided by delta y square. Option D, none of the above. So uh, this CFD formulation itself, I have told you, like, we have to first formulate our physical problem to mathematical equation, and then we have to convert that mathematical equation to algebraic equation. So this is the mathematical part and this is an algebraic equation. So here is like dou square u by dou y square is given. So how this differential equation can be converted to a algebraic equation, that we have to uh, understand the basics of differential equation. How, what is dou u by dou y or dou square u by dou y square? So here the distribution of y in y direction, sorry, distribution of u in y direction is what it is giving. So how we can discretize that, how we can convert into algebraic equation? So which of the following is the answer? You can try to do it by yourself and please inbox the answer. Okay, let me explain. I think some of you are having confusion. Okay, so let's start from the basic. So our actual answer is answer D, none of the above. So I will explain why. So first, please see this two-dimensional distribution of grid points. Here, suppose this is the point ij. So how the other points are located? So using Taylor series approximation to for a delta change in our actual value of u, then our equation becomes u of ij plus 1. That is, suppose this is the location of u, then u of ij plus 1 is the point here, and u of ij minus 1 is here. Because our question is in y direction, we need to find solution for dou square u by dou y square. So all we dealing is in y direction. So u of ij plus 1. So a delta increment along y direction will be u of ij. That is the initial u at point P plus dou u by dou y at ij into delta y. That is the grid spacing. That's the grid length. Plus dou square u by dou y square at ij into delta y square plus etc. Similarly, u of ij minus 1 will be u of ij minus dou u by dou y at ij into delta y plus dou square u by dou y square at ij into delta y square minus, here it will be alternating plus and minus. So the conversion of this dou square u by dou y square, that is, this will be lying here and here. We are taking this approximation, Taylor series for approximation, and we are trying to establish this thing. So if you are adding these two equations, then you can see by removing all those things, what we will be getting is dou square u by dou y square, that is 2 times dou square u by dou y square at ij into delta y square plus 2 times u of ij is equal to u I comma j plus 1 plus u of I comma j minus 1. So if I am taking these terms to the other side and dividing it with delta y square, the equation will become u of I j plus 1 plus u of I j minus 1 minus 2 u I j divided by uh, 2 delta square. So here, why it is not a? That's a answer question. Because if you see here, it is j minus 1 I. Also, this j minus 1 I or I minus 1 j is this terms is kind of showing the index of the location of that particular point, and it will depend on the uh, if you can see, this is kind of interchanged. But when we are computationally solving it, these uh, points have significance, because we will be, if you see, suppose in our first problem itself, we are dealing with a rectangular duct. So here, suppose this is x and y, then for a rectangle duct, x is not equal to y. So the discretization along y direction won't be equal to discretization along x direction. So suppose we are taking I for discretization along x direction and j for discretization along y direction, then interchanging these two uh, will give wrong answer. Because, like, suppose we are writing this equation, then we will be starting like I is equal to 1 2 3, or I is equal to n minus 1 to something. Suppose we have n um, terms here, then that will give you a wrong answer. So hope that is cleared. So you don't know if you have some issue with Taylor series expansion. I have given a detailed explanation of Taylor series here also. From this, you can see how the initial solution is coming. There I have taken Taylor series, taken for granted. If you want to explain me this, I can explain. Do you want me to explain the Taylor series also?
No, it's fine, I guess.
Okay, I will make it a quick explanation. So, with the Taylor series for f of x, we can take any point, we can take any function as a series. We can expand it as a series. So, assuming the grid points I as we have seen earlier, f of x is equal to f of xi. This is the actual equation or the expansion of Taylor series equation. So this f of x can be anything. It can be u, t, p, anything. So here it will be f of xi, that is like the property at that point p plus something, that is x minus xi, the variation plus that uh, gradient of change, dou f by dou x at I plus the higher order term x minus xi the whole square by 2 factorial into dou square f by dou x square plus etc. up to x minus xi raised to n by n factorial dou raised to n f by dou x raised to n plus higher order terms. So this will be the equation. So if we want to find f of x, this f of xi can be next time is f of xi plus 1. F of xi plus 1 can be written as you have only to replace all these points where there was xi before, you have to replace it with I plus 1. So you will get one equation here. Then again, if you replace that I with I minus 1, that is if you are moving leftwards. Suppose I direction, that is x direction. So advancing is the right direction. Going backwards is minus direction. So I plus 1 is kind of moving towards right. I minus 1 is moving towards left. So this you can achieve by replacing this x I by x I minus 1. Now this will be our second equation, from which, from equation 1, dou f by dou x, this term can be achieved by like this, because we are only bringing this term to the right side and rest everything is kept other side. And this higher order terms, we are, because we are only taking up to second order, and higher order terms, this is the things we are neglecting, because this can go to infinity and there can be any number of terms according to the level of accuracy you need. So this some portion we have kept as higher order, or some error or something that we are willing to give away. So this we can we will be truncating or dropping in the calculation. That is called truncation error actually. So that we are not going for, because we only need up to an accuracy of second order accuracy only we need. So we are anything higher than that uh, value we will be assuming as so can be neglected for our reasonable accuracy. So for a second order solution, the higher order above uh, second order can be removed. So from this, if you rewrite the equation, dou f by dou x I can be written as f of I plus 1 by f of I delta xi plus, here the other term also I have removed. So then it will be order of delta x. Our equation, our uh, accuracy of this dou f by dou x calculation will have a order of delta x. So anything in the terms of square order terms will be neglected. We will be only having the accuracy of delta x. That is called order of delta x. This is the order of truncation that we are removing. From which, if you are taking the from equation 1, we will get this. From equation 2, you will be getting this one. And adding and rearranging, it will become dou f by dou x is equal to f of I plus 1 by 2 delta x. So this is the approximation for dou f by dou x. That's the first order term. In our question, it was second order term. So that can be same of which can be used to get second order also. From that, if you rearrange it, we can get second order as this one. Hope everyone is fine with the equation. This I will be posting along with the video. You can get it from the shared folder. Moving on to next question. Consider a steady developing laminar flow in a circular pipe. Which of the following statement is true for this flow? Statements are velocity profile changes axially. Second statement, velocity profile changes radially. Third statement, pressure varies linearly in the axial direction. Fourth statement, pressure remains constant. Options are statement 1 and 2, option B, statement 2 and 4, option C, statement 2 and 3, option D, first only. Please inbox your answers. So, uh, this is what I have told about the first part of the CFD, that is the physics of the problem. Here, our condition is like uh, the particular scenario, it is the flow, our flow is steady and it is developing and laminar flow. So, these things, when we are modeling something, these kind of things should be properly addressed as in the equation. I mean that the mathematical modeling of the problem, or else in the boundary conditions. If not, our answers won't be correct. So let's see what is happening in a circular tube. So suppose this is the tube uh, in which the flow is happening, and this is the reservoir or the place from where the flow is coming from. So from where, when it reaches the tube entrance, it will be having, suppose I am assuming the flow will be having some uniform velocity. So uniform velocity profile will be like a rectangular, because all the flow lines will be having same velocity u. But once it uh, touches the entry or reaches the entrance of the tube, the boundary effects of the circular tube start to alter the flow. So this entrance length, or the effect of this circular geometry or the boundaries, will be exist for some region. That region is called entrance length or developing profile, developing region, not developing profile, developing region. And that developing region, the profile of the velocity is called developing profile. So if you see, the rectangular flow has been reduced to, it is kind of gradually changing, and it will become a parabolic flow. You might have studied that uh, velocity profile inside a circular tube is parabolic, but the transition from this rectangular to parabolic is what is happening between here. So this you can see these 2 points. It will have to move towards center, and somewhere here it will merge with each other, forming a parabola. So if you see the pressure along the axial direction is plotted here. The inlet pressure is constant. Once it reaches the entrance, it starts to steadily it changes abruptly, and it try to readjust itself. So if you can see, it is kind of uh, reducing, but not in a linear way. And after, once it is fully developed, the pressure drop is become more like in a linear fashion. So with this understanding, if you are trying to solve read the equation, you will get more clarity. Here first statement is velocity profile changes axially. Axially means forward direction. So in the developing region, I already told you, the rectangular uh, velocity profile will change to a parabolic one. So the velocity profile will change axially. That is true. The second one is the velocity profile will change radially. That is, it will be having uh, radial. That is, suppose this is the tube, this is the axial direction, this is the axial direction x, this is the radial direction r. So radially also it will change uh, because the near the walls the velocity will become zero, and towards the center it will be maximum. So from walls to the center point or axial uh, region, the velocity will increase. So there is a velocity change in the radial direction also, in the developing region, not in the developed region. So this is the key jargon here. uh, Once it is developed, there won't be changes in the axial direction. Also, the third point is pressure varies linearly. That we have seen that it is not varying linearly. And fourth uh, statement is pressure remains constant. That also is not true. So statement 3 and 4 is not true. Option statements 1 and 2 is true, which gives option A as a right answer. Moving on to next question. Consider an one-dimensional flow governed by dou square u by dou y square is equal to c over a height h. The interval h is divided into 30 equal segments. The upper wall move to the right at a speed of 1 meter per second, while the lower wall is stationary. The number of discretized equations are, options are option A 29, option B 30, option C 31, option D 28. So here is talking about a one-dimensional flow, and the interval h is divided into 30 equal segments. Something like h. This is divided into 30 segments. Suppose like we are 1, 2, like that. 30 segments have been formed. So the question is, what will be the number of discretized equations? Try to answer the question. You can inbox your answer. Uh, I have given you the clue. Try to uh, connect it with the third question and try to solve it. Let me drink some water. Okay, let's see. So, for this is a single one-dimensional domain. So, when there are n segment, there will be n plus 1 discretized points. Because you can see, if you want to divide into 3 equal parts, there will be 4 points. So, 1, 2, 3, 4, and this will be A, B, C. So, this will be the segments. So, this will be the nodes or points. So to discretize into 30 segments, you will be needing 30 plus 1, that is 31 points. And our question is like, uh, our question is the number of discretized equations you need. So we will have to solve for 31 points. But if you see here, the upper wall we have given they are already given the boundary condition. That is, the upper wall is moving at 1 meter per second and lower wall is stationary. So two conditions are already been given. So suppose this is the 31st and this is the first one, then this condition, that is here u is equal to 0 and here u is equal to 1 meter per second, that both those two conditions are given. So we will have only to write discretized equation for the rest, that is 31 minus 2, that is 29. So our answer is answer A. So these kind of questions will come in the exam also. Somebody was showing. So try to get that conceptual clarity. And also this is one fundamental thing when if you are try doing some uh, CFD equations and CFD code by yourself, then this uh, n segment and n plus 1 is kind of a first basic error you will face. That also same was valid when we discussed about the third question, that is the j minus 1 being placed at the first or second, that condition. Okay, so next question. The correct equation governing flow in a fully developed flow through a rectangular duct is option A, dou square u by dou x square plus dou square v by dou y square is equal to 1 by mu dp by dx. Option B, dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dp by dx. Option C, dou square u by dou x square plus dou square u by dou y square is equal to 1 by mu dp by dx. Option D, dou square w by dou dou x square plus dou square w by dou y square is equal to minus 1 by mu dp by dx. So this one is also a little tricky question. Try to answer it. Try to inbox your answers. Okay. So, uh, first confusion anyone can have is like, here it is saying about which is the correct equation for a fully developed flow, but it is only mentioned it is rectangular duct. If you remember in the first example of our first video, the flow is happening in z direction. So first confusion anyone can have is the direction of flow, which is the axial direction or which is the direction of flow. So the best bet is to check the denominator of the pressure type. That is, here if we check all the uh, in all the options, it is in x direction. So the equation is in x direction. The fully developed flow we are talking is about in x direction. Then if you take the momentum equation in x direction, then it will be something like this. This will be the fully equation of fully developed flow through a in rectangular coordinates, that is Cartesian coordinates in x direction, and it is already said that fully developed flow in axial direction. So it is fully developed in x direction. So we will be only having u component, that is small. The v and w components won't be there. So we will be only having u component, and it will be a function of what, y and z, that is other two coordinates. Suppose x, y, and z are the coordinates. Then uh, velocity components are u, v, and w. Since it is fully developed in x direction, only u will be there, and it will be a function of y and z. So applying this uh, thing in our solution, and also it is said that it's a steady flow, so this term will also go. So, and also if you neglect body forces, this won't be there. Then rest, if you rearrange, you will get option B as our answer. So these kind of definitely have to do with the questions. Hope everybody understood the concept. Moving to next question. Next question is, consider a fully developed laminar flow through a square duct of side L through a rectangle duct with width to height ratio of 2 such that both of them have same cross-sectional area. If some fluid flows both the ducts at same volumetric flow, which of the following statement is true about the two flows? So here the condition is you are being asked to compare between two flows. One is happening in a square duct, other is happening in a rectangular duct. Rectangular duct, and assuming same cross-sectional area, what will, and same volumetric flow, which of the statement will be true? The statements are, the governing partial differential equations is the same. Second statement, the wall boundary condition are the same, though these are applied at different locations. Statement 3, the flow domains is the same. Options are A only, option B, statement 2 only, Option C, 1 and 2 only. Option D, 1, 2 and 3 only. Sorry, I missed and 1 here. 1 only, 2 only, 1 and 2 only, and last one is all of them. Just try to answer the question. Okay, so um, from the statement itself, by our discussion this far, we can say that the first will be right, because fully developed laminar flow. This is what happening inside both conditions. So our governing partial differential equation should be same. And second statement is saying the wall boundary condition are same, though these are applied at different locations. And also the two instances are, one is, the only difference is one is square and other is rectangular duct, and there is no uh, inference of any lateral flows or uh, flow from the other sides. So the wall will be having zero velocity or no slip boundary condition. So this will also true. And third statement, the flow domain is same. So we can say the flow domain is not same. Even though if they have same cross-sectional area, the flow domain is not same, because one will be having a square domain, the other will be having a rectangular domain. So our answer is 1 and 2 only. Sorry, 1 and 2 only. That is our option C. Moving on to next question. So this is a case based on which multiple questions will be there. First, we will check what is the case. The case is, you wish to solve a problem involving steady state heat condition with a source term in the case of one dimensional flow. So in the question we can get at least three things. That is, the flow is steady state heat condition, and it does have a heat source term, and it's an one dimensional problem. So our uh, equation becomes, fundamental equation becomes k into d square t by dx square. That is second order distribution of t in x direction is equal to q. That is flux, where k is the thermal conductivity, t is the temperature, q is the volumetric heat generation rate. For this case, answer the following questions. Keeping this on mind, we have to answer the following questions. First question is, for the equation for the equation 1 to be dimensionally consistent, the units of q, that is source term, should be what? Which among the following? Where j in the option is joule. So option A, joule only. Option B, joule per meter cube. Option C, joule per meter square second. D, joule per meter cube second. So we know for an equation to exist, it should be dimensionally consistent that is the dimensions of the left hand side should match the right hand side. So for the from this equation, what will be the dimensions of Q, that is the volumetric heat generation rate? You can inbox your answers. Please inbox your answers. Okay. So from the equation, Q is equal to K into d square T by dx square. So K is the conductivity, which is watt per meter Kelvin. T is in Kelvin and X is in meters. So substituting all those, watt per meter cube will be there. Watt is joule per second. So the answer is joule per meter cube second. And our answer is answer option D. And funny thing is, if you see this statement itself, you can answer it. It's a volumetric heat generation rate. So it's like volumetric. So there should be a meter cube term, and it's a rate. So there should be a second term, and it's a heat. So heat is an energy. So joule. So you only need to find a combination of these three. That is only for option. That is option D. Moving on to the next question. For equation 1 to be one dimensional, the term Q can be of which form? So the statement of Q to be the equation 1 to be in one dimension, which of the following should be true? Option 1, Q is equal to constant. Statement 2, Q is a function of x. Statement 3, Q is a function of t. Option 4, Q is a function of x and t. Options are statement 1 and 2. Option B, statement 1 and 3. Option C, statement 1 and 4. Option D, all of the statement. You can inbox your answers. So the direct question, to be keep in one direction, it should be either constant or function of x. And if you see, the condition is telling steady state, so there is no variation in with respect to time. So giving uh, q, the volumetric heat generation, as a function of time is not acceptable. So this option, third option and third statement and fourth statement cannot be accepted, and only these two statements can be accepted. So option A, that is statements 1 and 2, is true. Next question. Which of the following is an admissible extension of equation 1 to steady state heat conduction in two dimensions? So in equation 1, we are only talking about uh, one dimensional equation. So how can we extend that to a two dimensional equation? Statements are uh, k into dou square t by dou x square plus dou square t by dou y square is equal to q is equal to q of xy. Second statement, dou square t by dou x square plus dou square t by dou y square is equal to 1000. And uh, third statement, dou t by dou t is equal to alpha dou square t by dou x square. Our options are statement 1 only, that is equation 1 only, option B equation 2 only, option C equation 1 and 2, option D all the three equations. Please inbox your answers. So our answer is option B, that is uh, the heat distribution is equal to some constant, because this will become complex. This two-dimensional heat generation equation, heat generation term will become complex. So admissible extension is equating it to constant condition. And here if you see, it's a time vary, not it's not at all no longer steady. It is going to uh, time variance. So option B, that is second equation, is the admissible extension of the equation. Next question. A client has produced a new catalyst that would improve the rate of catalytic chemical reaction and wants you to check it out using CFD simulations. For this problem, which of the following statement is true? Okay, before going further, in our course, we will be dealing with a little bit of chemical reactions in the flow also. So we'll have to, it's better to learn that side of the fluid flow also. Species transport also are being discussed in our course. Okay, so options are option A, you expect CFD to give reasonably correct solution. Uh, Option B, you expect CFD would not be much use because you think the reaction rate should be specified. Option C, you expect CFD would not be of much use because you think flows with chemical reaction cannot be handled through CFD. Option D, you expect CFD would not be of much use because you think flows with catalytic chemical reactions cannot be handled through CFD. So you have a scenario where one of your client has developed a new catalyst and that client needs your help in simulating a catalytic chemical reaction for the same. So which of the following statement is a reasonable expectation? Please inbox your answers. So here our option B is the right answer. We think this will be the similar to your first question, but here uh, the problem is of uh, catalytic chemical reaction simulation using a new catalyst. But for doing a CFT simulation, we need a proper understanding of the physics and also need the material properties also. So to simulate the material property, to simulate the catalytic reaction, we need the material property or other chemical properties of the catalyst, which is not mentioned here. So option B, that is CFD may not be of much use because it's a new product what he is asking to do, and unless that catalyst is tested and you have the material properties or chemical properties of that particular catalyst, you can't give that as an input to your CFD. So uh, without that properties, we can't expect to get a reasonably good answer from CFD. So option B is our answer. Moving on to next question. You wished to solve a set of linear algebraic equations written in the form of Ax is equal to b matrix form, using Gauss-Seidel method. This method will converge if which of the following conditions is satisfied. So, as we have discussed earlier, the mathematical equations will be converted to algebraic equation, and algebraic equations, the set of system of algebraic equation can mostly be written as Ax is equal to b in matrix form, where A is the coefficient matrix, x is the variables, and b is the right hand side. So for this coefficient matrix A, how what what are the needed properties of this coefficient matrix A? sorry sorry, excuse me. uh, for Gauss-Seidel method to work, what should be the properties of matrix A? Statement 1, matrix A should be non-singular. Option B, second statement, the spectral radius of A must be less than 1. Third statement, matrix A is irreducible and diagonally dominant. Options are statement 1 only, option B statement 2 only, option C statement 3 only, option D 1 or 2 or 3, option E 1, 2 and 3. Please inbox your answers. So the needed property for matrix A is this one, and third statement, that is it should be irreducible and it should be diagonally dominant. Then only we can use Gauss-Seidel method to solve the system of linear equations. Moving on to next question. An ideal fluid is option A obeys ideal gas law, option B has constant thermophysical properties, option C has zero viscosity, option D none of the above. So the question is, which of the following statements best explains an ideal fluid? You can inbox your answers. You might have heard of ideal gas law and ideal gas, but the ideal fluid, by definition, is one which has zero viscosity, that which is not viscous at all. If there is a fluid is there such that there is no viscosity or friction in between the fluid layers, such a fluid is called ideal fluid. Our answer is option C. Next question, an example for Newtonian fluid. So the question is, which among the following is can be taken as an example for Newtonian fluid? Option A, air. Option B, mercury. Option C, glycerin. Option D, all of the above. Let's try to answer the question. You can inbox your answer. Yes, answer is right. Air, mercury, and glycerin, all of them can be treated as Newtonian fluid. Next question. The boundary layer flow approximation applies to which of the following? Option A, only to very low Reynolds number flows. Option B, only to high Reynolds number but still laminar flows. Option C, only to turbulent flows. Option D, to both B and C. So the boundary layer approximation concept in fluid mechanics is applicable to which of the following? Try to answer the question. Is right. Option D, that is to higher Reynolds number flows as well as turbulent flows, we can use boundary layer approximation. Moving on to next question. Which of the following contributes to the viscous drag over in a flow over a sphere? So which of the following factors influence the viscous drag in a flow over the sphere? Option A, only wall shear. Option B, only pressure variation. Option C, both. Option D, neither. So we have a sphere and flow is happening over it. So which of the following elements or terms will contribute to the viscous drag over the sphere in such a scenario. Only wall shear stress, only wall shear, or only pressure variation, or both of them, or none of them. Yes, true. Both wall shear stress and pressure variation will contribute to the viscous drag in a flow over the sphere. Then our option is option C. Moving on to next question. In a laminar fully developed flow through a pipe, which of the following is correct? Option A, axial pressure variation is linear. Option B, radial pressure in the profile is linear. Option C, radial pressure profile is parabolic. Option D, pressure is constant. So, if you recall the flow through the circular pipe we have discussed earlier, which of the following is true for the flow in the fully developed region of the pipe? Options are axial pressure variation is linear, radial pressure profile is linear, radial pressure profile is parabolic, pressure is constant. Our answer is axial pressure variation is linear, option A. So if you have remember the graph like P and x direction, that is axial direction. So the pressure will be so this will be the developing region. This is the developed region. This is the entry for entry region. So if you remember the graph, then you will see that here it is kind of mostly constant, and then it changes once it approaches the flow. Then in developing region, it is not. It is kind of logarithmically changing, or not exactly logarithmic. It is changing, but in a non-linear fashion. But once it has fully developed, then the axial variation of pressure is a linear function. And for radial distribution of pressure, it is not linear and also not parabolic. It will depend on the other conditions. And also it is not constant. So only condition for fully developed flow the what is for sure, the axial pressure variation will be linear. So our answer is option A. Moving on to next question. In a steady incompressible flow through a converging diverging nozzle, the pressure at the exit section is, options are the highest, option B the lowest, option C lower than the inlet, option D same as that of the inlet. So for a inlet and outlet. So what will be the pressure at the exit section? Assuming this is a converging diverging section. For a converging diverging nozzle, the diverging part will be much longer than the converging part. So what will be the pressure at the exit? Is it the highest, lowest, or lower than the inlet, or same as that of the inlet? You can inbox your answers. Our answer is option C, lower than that of the inlet. The key parameter here is incompressible flow. If it was an compressible flow, then it would have changed. It would have depended on the inlet flow velocity and the Mach number. So uh, here it is specifically mentioned as incompressible flow. Then uh, we can for sure say that the pressure at the exit will be lower than that of the inlet. Moving on to next question. Over 50% of the time spent in an industry on a CFD project is devoted to the definition of the domain geometry and grid generation. Which of the following is the reason for this? Option A, more grids will give better results. Option B, calculation time is directly proportional to the number of cells. Option D, to generate non-uniform grids. Option D, to generate optimal grid, which is a compromise between desired accuracy and solution cost. So first, one statement is given that the 50% of the time spent in the industry, CFD industry, is devoted to the definition of geometry and grid generation. What might be the reason for this? Try to answer the question. You can inbox your answers. uh, no, the apt answer among the following is D. So it is true that more grids will give better results, but we can't keep on for an industry. We can't keep on increasing the grid points because as the number of grid points increase, the calculation time as well as the computational cost will increase. So the, the for industry or whatever may be the reason, we will be try to optimize. So optimization is between desired accuracy and solution cost, that is solution time or the cost spent over it. So our requirement is to uh, find an optimal grid. So in CFD there is something called grid independency, that for your CFD results to have reasonable accuracy or uh, trustable accuracy, uh, it should be uh, PF grid independent, that it won't affect. Suppose you are solving some CFD problem and the number of cells in that particular mesh should not affect your accuracy. So that is reached by this grid independency test. So you have to keep on increasing this number of cells, or the you have to refine the grid uh, to a point somewhere it is not much varying with respect to the number of grids. Suppose this is the number of grid points, and this is the some variable you are interested in study. So for uh, the grid inverse studies, like if you are doing the same, repeating the same uh, calculation with different set of grid points, then it will be like increasing to some point, then it will reach a plateau where the change will be very less. There will be still changes, but it will reach a point where the rate of change will be very less. So you have to find some uh, number of grid points in that range to show that your study results are reasonably good. So such a test is called grid independency test. So answer for the question is option D. Moving on to next question. In a turbulent flow through a rectangular channel, if the flow rate is doubled, then the pressure gradient is likely to become which of the following? Option A remains the same, double, quadruple, or 16 times higher. Can inbox your answers. Okay, our answer is option C. That is, it will quadruple. It will become 4 times higher. So that's all for today's section. Thank you for attending. Thank you for joining.